give you the exact same model. They're mathematically equivalent to each other. Yeah. Any questions? Yeah.
I think I'm a little confused. So usually if you do the just the dual of this first problem, you should have minimization over W, and then the second time you should have a maximization over lambda bigger than 0. Why do you have like minimizing over W in that?
So that depends on the sign of your constraints, like less than or equal to, or greater than or equal to. So I mean.
But it's like smaller.
Well, then, so it's either this minus C, or it could be C minus this, or it could be minimizing over lambda, maximizing lambda. You could flip it.
Because of the sign.
Yeah, you could flip it. There's multiple equivalent ways to write this, right? It could be C minus this, in which case I have to maximize over lambda. And in fact, I should double check. I may have written this slightly correctly, but there is a way to write it such that it looks like this. It's a minimization problem over both W and M.
And then lambda bigger 0 should be also bigger, right? Somehow.
Lambda equals 0.
Bigger than 0. Like the dual constraint.
Lambda bigger. Oh yeah, sorry, I did not actually. For simplicity, I did not put in the constraint that the lambda needs to be obvious.
Oh.
Yeah. So I did omit a few details, like there's some constraints like lambda need to be actually the main constraint. The main thing I omitted is the fact that lambda needs to be at least 0, and without that you don't get this condition, right? But the main point of this slide is to show that these two optimization problems are equivalent. There's a one-to-one mapping between this optimization problem and this optimization problem. For every C, excluding degenerate cases, for every C maps to a unique lambda, and that gives you the same W back. So if I were to do cross-validation over choices of C, this is a type of model class that we talk about in class, right? It's like a space of models, right? So this is the type of model class we talk about in class. This is not necessarily a model class. It's just an optimization problem, right? This is a model class. We minimize training loss within some model class. And so how you use this during training is you would do cross-validation or some other validation, try a bunch of different C's and see which one gives you the best solution. Suppose in the limit you try all possible C's. Because there's a one-to-one mapping excluding degenerate cases of all C's of a C to a lambda as shown by this Lagrangian, then we could, instead of doing this, which is harder to solve because of this constraint optimization problem, we solve this, which is unconstrained. We just try all possible lambda, or a large choice of lambda, and we've equivalently solved the same validation over model classes as if we had done this. And the reason why we do this is because this is mathematically, or computation more convenient to solve. So in practice, people minimize the training loss, a trade-off between training loss and regularization. The way you should think about it as being consistent with what we've talked about in class is that is mathematically equivalent to solving just the training loss over some constrained model class. And that connection is derived by the Lagrangian. Yeah.
The last equation, I think it should be minus lambda. The partial derivative of L must be.
Okay. You're saying what?
The partial derivative of L must be equal to minus lambda.
It's possible that you're right. I'm pretty sure I double check this. Okay, I'll triple check after class. But I hope that doesn't confuse the point I'm trying to make. If I got assigned, I might have gotten assigned first. I don't think I did, but I'll triple check after class. Any other questions? Yeah.
Why people not directly minimize the Lagrangian instead of solving the recognized equation?
Minimizing this?
Yes.
You can if you set C.
So what's the complexity between the recognized training and the minimizing the Lagrangian?
What is the complexity?
Yes.
So I should mention that all three of these have the same number of tuning parameters, right? This one is a C, this one's a lambda, this one is a C.
But for example, to minimize Lagrangian, you have more parameters to tune because you have an actual lambda.
Yes, that's, I see. I see what you're saying. So no one actually, okay, so it's definitely the case that this is more computation convenient. There's no question here. It's unconstrained, right? Like you did this for homework 1, or we did this for homework 1. Adding this part is pretty straightforward, right? So that's definitely the case. If you want to solve this one, suddenly you have to ask what happens if W goes outside C. Typically, if you do it via stochastic gradient descent, you do a projection back onto, as I showed in the sort of the animation. And I don't think anyone in practice actually does this when they do gradient descent. No one does this with gradient descent. With stochastic gradient descent, excuse me.
So what's the reason for that?
I'm sorry?
What's the reason for that?
Well, you're minimizing over W and lambda, and there's no reason to do that if you get the same answer by minimizing over W, is the practical reason. I mean, they all get you the exact same solution. Why solve a more complicated optimization problem? No, it's like I have some for loop to do something, and for kicks, I'm going to write another for loop outside of it just to do it 10 times. It's just, yeah, people don't do it in practice. I mean, people do exploit the Lagrangian for, if you're into advanced optimization, there's a notion of a primal dual type of, anyways, people do exploit it for more complicated optimization problems. So the Lagrangian is still an important concept in many optimization problems. I'm only using it here to demonstrate the connection between traditional notion of model class that we've been talking about in class versus what people would typically do in practice. Right? I'm demonstrating the equivalence between the two. And for the purpose of this class, we're just primarily using stochastic gradient descent. We don't need to know more advanced topics related to the Lagrangian. Although if you're interested, there are links off the course website with reading material for advanced topics. Yeah?
Just a question. So as C becomes smaller, when lambda becomes bigger, right?
That's right. There's an inverse relationship between lambda and C.
So this maybe explains like Gaussian question before. So when C gets bigger, the circle of admitted W's gets bigger.
Yep.
And at the point where it includes us the
The
global
optimal
minimum,
solution. Yep.
global
Yeah, that's
minimum
right.
stops growing.
Yeah.
So you have like the sharp kink.
Yes. And that applies.
It's only because of the coordinate. So if you have that same form, probably you still.
Let me think. It's an interesting point.
It seems to come just from the regularizer and not from the objective function. So if the regularizer is the same, you should have this behavior all the time.
Regularizer is the same. You should have this behavior all the time.
Because at some point you would hit the global minimum and then it would stop growing.
Okay, I agree with you. I agree with you if we were able to do a very fine-grained discretization of C's and lambdas. As C's become very large, lambda becomes very, very, very small. Lambda goes 0.0, 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, 10 to the minus 5, 10 to the minus 10. And typically in practice, no one does that. I think the reason why you saw it so quickly, a simple training example is because of how simple the learning problem is. I would agree with you that is what you said is true. I'm not sure that it completely explains the effect specific to the example I gave. Yeah. Well, it's an interesting point. I should think on it more. Just to recap, so ridge regression is L2 regularized least squares regression, which we show is equivalent to a norm constrained to minimizing square loss over a norm constrained model. Right. So there's a one-to-one relationship between some C here, which defines the model class, and this lambda here in this optimization problem. Large lambda gives you more stable predictions, less likely to overfit to the training data, If your lambda is too large, then you'll underfit the training data, in which case you won't do well on the test set either. We'll go to the last one this way.
Why is it called a ridge regression?
Why is it called a ridge regression? Because the mathematical formula for the closed form solution, I'm gonna write something on the board. Okay, so there's a closed form solution to, I believe this is the answer, because I think the terminology comes from people in the statistics community. So I could be a slightly, don't take everything I say as canon, complete canon. Maybe I should just preface this, okay? So the closed form solution for least squares regression is XX transpose inverse XY transpose, something like that. And when you do ridge regression, you just add a ridge of a diagonal term to the closed form solution. So you add this matrix. It includes as a matrix of a diagonal identity matrix times lambda, and they call that a ridge. And that's related to my next point, actually. Another way to think about ridge regression is that we're just hallucinating data points, right? What does that mean? Well, this is the ridge regression problem. The gradient with respect to W looks like this, right? Okay, is there any way to interpret this term, which is the gradient induced by the L2 penalty? Is there any way to interpret this term as a square loss of some training example? Can we define an artificial synthetic hallucinated training example such that this gradient is the result of that? Yeah.
Training example at the origin.
Or
I mean, where the
that's almost correct. I think maybe I primed you to give the wrong answer because it's not a single training example. It's one training example per dimension in your feature representation. So you might have gotten the right answer had I not led you the wrong way with the way I phrased the question. So we're going to hallucinate D training examples, one per feature dimension. And it's going to look like this. E here is the basis vector, so it's 1 at the dth component and 0 everywhere else. And it's going to look. And so this is, you can think of this as a feature, right? It's a feature vector that's that is non-zero at exactly one component and 0 everywhere else. And the label is 0. The regression target is 0. And you could actually check for yourself that with this set of hallucinated training examples, and you treat these as training examples, the induced squared loss gives you this. And if you do the sort of mathematical matrix manipulations, this you can manipulate into a ridge of a diagonal matrix with multiplied by lambda. Any questions?
What did you say? So you said at these specific points, if I take the gradient, then I get the same thing that I had before. Is that what you're saying?
So imagine this data point, right?
Yeah.
Imagine D of these, right? One per, right? So I have training loss that looks like this, right? So I pretend that these are training examples, right?
Okay.
I'm hallucinating training examples.
Sure.
And so I have D of these, I W transpose this basis vector multiplied by the square root of lambda, the regression target is 0. What is the gradient of this with respect to W? Well, if you just
Sure, do it.
goes like this and you just do this.
Okay.
And then this is exactly the gradient of the two norms. They're equivalent. They're mathematically equivalent. So regular ridge regression is like if you take like a hallucinating training example point of view, it's like I'm saying, okay, in the absence of overwhelming amounts of training data, I'm just going to pretend that the regression target should be 0 for each of these dimensions. They're mathematically equivalent. Yeah.
To clarify, lambda here is a scalar, right?
Lambda is a non-negative scalar.
Would you ever want to think of lambda as a vector?
So you care more about regularizing certain dimensions than others?
Exactly.
Yeah, you can absolutely do that if you want to. You have to have prior knowledge that makes sense. In the absence of any other information, you have no reason to believe that you should regularize one dimension more than another.
But if there was like some theoretical
or you have domain knowledge, right? You're like, okay, I know that this is probably not. I mean, I'm hand waving a little bit, right? But like I know that this dimension is probably not that useful. I'm just going to regularize it more. Okay. So next up is an extension to multitask learning. So multitask learning is the problem of jointly learning to predict for two different prediction tasks simultaneously. So for example, let's say we want to train two different spam filters, one for Alice and one for Bob. Now, we have limited training examples for both, right? But we're going to make the assumption that a good spam filter for Alice will also be a good spam filter for Bob, right? What that means is that a good W for Alice will get reasonably good accuracy for Bob, and vice versa, right? So we have two training sets, and indexed by superscript 1 and superscript 2. And the number of training examples is relatively small. So option 1 is to say, okay, well, we're going to ignore the fact that we think Alice and Bob are similar. We're going to train a separate model for each one using their separate training examples, and go from there, right? The consequence, of course, is that both models have relatively high error because the training sets are small. We could say, okay, well, Alice and Bob, let's just treat them as a single person, right? Like a global, we're going to train a global spam filter for everyone, right? Then what we would do is we would sorry, I jumped ahead of myself. The two is to train jointly, right? We're going to train a spam filter for Alice and a spam filter for Bob, right? Of course, this objective function doesn't accomplish anything because Alice and these two objective functions completely decompose additively, so you could solve them separately. So you get the exact same solutions as if you had solved them separately. So what multitask regularization says is it's another form of regularization. It's a generalization in this particular case of ridge regression, which basically says I want neither W or V to be too complicated. That's the ridge standard regularization term. I want to minimize this training loss over my two populations, and I want W and V to be similar to each other. And so here I'm penalizing the square distance between W and V. So this is one instance of multitask regularization, where how much we prefer W and V to be close to each other is controlled by this new regularization term gamma. And so here's an instance of test loss on task 2 for different values of gamma. And again, this is from synthetic data that I created, where the two prediction tasks are close to each other. So if gamma is low, that means these two become basically independent training tasks, right? In which case, the Alice model just learns on Alice's training data, the Bob model just learns on Bob's training data, and we just make separate predictions, and you get this error on the test set for Bob. As gamma increases, we say, okay, now we're going to regularize Alice and Bob to be close to each other, right? And what that means is that they can share, what that essentially means is that whatever training error, whatever gradient is induced by the training error on Alice will induce a gradient on Bob because of this component, right, indirectly. That's what's going to happen. And so now we see that the training test loss gets lower, because we're sharing data, and sharing data has some value. But if gamma is too large, then we're effectively treating Alice and Bob as the same person, right? In the limit where gamma is infinity, we suffer infinite loss as soon as W does not equal V, right? So it's just equivalent to just dumping all the training into a single task and training a single model. And it turns out to be pretty bad, right? Because Alice and Bob are actually different people. They have different preferences. So a larger gamma helps, but the tasks are not identical, so you don't want the gamma to be too large. And so in practice, we often find that they're not actually a single big training machine learning problem with a single large training set. There's often many similar training machine learning problems with related training sets and related solutions. And this is one way to exploit that and gain statistical strength from multiple smaller training sets that are related. Any questions? Okay, I'm going to jump into the last topic of the day, Lasso, which is L1 regularized least squares regression. So L1 regularizing square regression, just remember that L1 is regularized using the L1 penalty on the weight vector rather than the L squared L2 penalty, so this is ridge regression, right? And so if we just look at what these L1 and L2 penalty look like as the weight vector deviates from 0, you know, L2 is, squared L2 is quadratic, obviously, and L1 is the absolute value, so it looks like this. Okay? And so what does that mean? So that means that the decrease in penalty for L2 from a component of W, for simplicity here, let's assume W is one-dimensional, from square root of 2 to square root of 1 is equal to the decrease in penalty of W from 1 to 0, right? Because this is a reduction of penalty of 1, and this is also a reduction of penalty of 1. On the other hand, for L1 penalty, it says, well, the decrease in regularization penalty for W from 2 to 1 is equal to W from 1 to 0. So this is the type. These are the sort of conceptual thing that you need to keep in mind when you're comparing the behavior of different regularization functions, right? What does the curve look like in terms of relative reduction, right? L2 penalty says because the penalties grow quadratically, I really don't want very large values. But I don't suffer penalty for very small values. I don't suffer much penalty for small values. L1 says I suffer the same amount of penalty, penalty reduction no matter if I'm small or large. Like if I'm small and I grow a little bit, I suffer the same penalties. If I'm large and I grow a little bit. L2 says if I'm large and I grow a little bit, I suffer a lot of penalty. If I'm small and I grow a little bit, I suffer a very small amount of penalty. So I briefly mentioned the subgradient in the previous lecture. The L1 penalty is not differentiable at the origin specifically. And so when you do gradient descent, stochastic gradient descent of the L1 penalty, you typically, the simplest thing to do is to exploit a concept known as a subgradient. And the subgradient is basically, in the case where the subgradient, the function is differentiable, the subgradient is a set of vectors. And in the case where the function is differentiable, the subgradient is exactly just a singleton set, which is the gradient. In the case of L1 at the origin, which is not differentiable, the subgradient is a set of vectors. And in particular, in this one-dimensional case, it's a set of slopes, because that's the gradient in the one-dimensional case. It's a set of all possible slopes bounded between -1 and +1. Right? So for L1, if the W component is negative, then the slope is -1. That's the gradient, because that's the gradient of the slope at this point. The gradient of the L1 penalty at this point. The gradient of the L1 penalty at the positive point is +1, and at the origin, it's anything bounded between -1 and +1. That's what's defined in this set. So in other words, all of these for convex functions that are non-differentiable, the subgradient are all possible slopes that lower bound the function. So, what does the gradient look like for the penalty term? For L2, it's just twice the weight vector, right? So as the weight vector increases, the gradient magnitude increases. For L1, if it's over here, it's just a constant. If it's over here, it's the same constant with a different sign. And then if it's down here, if it's at the origin, it's a continuous range of possible values. They're all valid. Okay, so let's visualize what this looks like in terms of Lagrange multipliers, right? So it turns out that L1 regularized least squares regression, a Lasso, has a one-to-one relationship with minimizing squared loss subject to an L1 norm penalty, right? And so we get the same sort of behavior as before as induced by the loss function. This is the L2 penalty, and the optimal solution for L2 is here. And for L1, so all possible W with L1 norm, this should be less than or equal to. Less than or equal to C is the set of all W within this tetrahedral. So in particular, the norm at a non-corner is the standard norm, and the norm at a corner is all possible norms, continuous range of norms. So if we're at this point and we induce a gradient on the loss and we project down to the feasible set defined by this, defined by our constraints, we get here. And it turns out, and for this example, that you'll just keep going if you follow the gradient until you get to this corner. And it turns, and at this corner, there exists, at this corner, this gradient, it points this way towards the optimal minimizer of this loss function. And the set of possible gradients, subgradients, normals at this corner is the set of all possible norms in this range. And it turns out that one of those norms is aligned with the norm induced by the loss function, and therefore we're at an optimality condition. So the optimality condition for L1 regularized gradient descent, which is L1 regularized least squares, excuse me, which is equivalent to L1 constrained squared error reduction, is defined by having, it has the same definition. You're at a point on the boundary where the gradient induced by the training loss is aligned with the gradient induced by the normal tangent to the boundary of your feasible class. And if you're at a corner, any possible subgradient norm that is that can align with this is the sufficient condition for optimality. So what does that mean? That means that the solutions to this optimization problem tends to be at the corners. Right, you just follow this gradient, you move this way, follow, move this way, follow this way, and suddenly, once you get to a corner, suddenly now the gradient is aligned with the norm, and you're done. What does it mean for the W to be the solution of the W to be tend to be at one of the corners? Well, it means that the most of the, so for example, at this corner, the component of along the x-axis, the feature corresponding to the x-axis, excuse me, the feature corresponding to the y-axis is 0, right? At the corners, many of the components of the weight vector are 0. So this is known as sparsity. A weight vector W is sparse if it's mostly zeros. And you can measure the sparsity level by the number of non-zeros in W. Sparsity is often a desired property in many applications. And if you think about it, if I want W to be mostly non-zero, mostly zeros, then I can just minimize the L0 norm, right? L0 norm says I incur a penalty of 1 if for any dimension of W that's non-zero. So why don't we use L0 regularization instead of L1? Any ideas? I'm sorry?
Not convex.
Great. It's not convex. It's also not continuous, right? Because the L0 norm says the norm is 0 and then suddenly jumps to 1 as soon as the component is non-zero, right? So it's not continuous, therefore not convex. So L1 is known as the convex envelope of the L0 norm. What that basically means is that people use it in practice to induce sparsity, and it's one that people know how to optimize. So why is sparsity important? So there's one aspect of why sparsity is important is in terms of computational memory efficiency. You know, suppose our feature vector is 1 million dimensional. Do you really want to store a million numbers in an array to model your feature vector, to model your model vector? The answer is probably no. And if your weight vector is sparse, then the memory requirements of your storing your weight vector is linear in the sparsity of your weight vector, not in the dimensionality, not in the explicit dimensionality of the feature representation. And for very large feature representations, which gets used in practice all the time, this is a very important consideration. So many models in practice are sparse. The dot product, by the way, is also more efficient, right? Because now you're just like traveling through a linked list type thing, as opposed to doing a for loop over 1 million numbers. And sometimes, we think that the true W is actually sparse. Right? We think that the dimensions of the feature vector that really matter in making these predictions are few and not many. And so we use Lasso to recover those non-zero dimensions. And so in that case, people have studied Lasso a lot from a theoretical perspective. And they have this guarantee. This is sort of the simplest guarantee, the standard simple guarantee that people have derived. And there are other guarantees that look like it. And if you're interested in details, there are some links that you can read about this in detail. And the basic idea is as follows. Suppose the data was actually generated from a sparse vector, right? W star is sparse. Then, so long as the lambda is sufficiently large, excuse me, as long as the lambda is sufficiently large and larger than some threshold that decreases with the size of the training data, then with high probability, the support of the non-zero, so the non-zero entries of W is bounded by the non-zero entry, is contained in the non-zero entries of the true model. What does that mean? That means if we use Lasso and we find a W that's non-zero, and we have enough training data to be physically confident, then we can be confident that, and if the true model was actually a sparse linear model, then we can be confident that we have no false positives. Right? If we found an important weight vector, it is actually important.
So you saw a question, how sparse does something have to be to be considered sparse? So
It's a great question. And as any question like that relates to what people use in industry, the answer is extremely fuzzy. Yeah, I would say 1% is sort of a rule of thumb. Like, you know, if you have a million dimensional feature vector and it's 10,000 non-zero entries, I would say that's sparse. Maybe 0.1%, something like that.
well, that's pretty sparse.
Yeah. Yeah, yes. Okay, so just a little pictorial example. This is one of the, unfortunately the visualization is a little hard to see. So it's the same training set, and what I'm visualizing is, so the x-axis is the value of the weight vector of the first dimension, and the y-axis is the weight vector, value of the weight vector corresponding to the second dimension. And you know, as you increase as you decrease lambda for L1 and L2 regularization, both weight vectors go up, right? So this visualization is a little bit confusing. So each point on this curve corresponds to a different choice of lambda for L2 regularized least squares regression, and the x and y corresponds to the two feature points. Right? And so let's just zoom in on the inside. So up here, you know, remember that L2 regularization really penalizes large W. So even as you make lambda small, it still doesn't want W to be very large because it has a quadratic penalty on the size of W. Right, so both the first component and the second component not very large. L1 regularization says, well, you know, I put the same amount of penalty, so you know, it could just grow linearly as you decrease the size of lambda. But you know, if you sort of zoom in here, which I guess for this specific training example, I should have tried a more concentrated range of lambda in this region. But if you zoom in here, you see that lambda, for some choice of lambda large enough, the weight vector corresponding to male, its value goes to 0. So we care more about age, right? And then for choice of lambda within this regime,